capacity, online people. So AFL, and we're going to work through our second FRQ on our AFL. So if we look at that, the information that it gave us, it asked us to calculate the amount of heat needed to purify 100 moles of aluminum. Remember, when you're dealing with your numbers, I would write down 1.00. So if you write 1, you're likely to think it only has one significant figure. But if you put 1.00, that'll help you to remember it has the 3 significant figures. So make sure you write them all out. So we're at 298 Kelvin. And then it says we're going to melt it. And the melting point is 933 Kelvin. And then the molar heat capacity, which is very similar to your specific heat, just in moles instead of grams, is going to be my 24 joules per mole times Kelvin. And then we know the heat of fusion, so we're told, is 10.7 kilojoules per mole. So that's all the information they gave us in the problem. So far, so good? Okay, so a couple things that people seem to be tripped up about, where we were given our temperatures in Kelvin instead of Celsius. One thing I want you to think about in this is we're finding the change in our temperature. So it really shouldn't affect you in any way if it's degrees Celsius or Kelvin. You're still finding the difference in the two values. And so since Kelvin and Celsius are, you would just subtract your values to switch between those two anyway, your difference will be the same no matter what your unit is. So that shouldn't have made too terribly of a different impact on you, other than it might have just freaked you out for a second. And then same thing we were talking about with our specific heat that just gave it to us in moles. So we're in moles here and we're in moles here. Our units match. So that's not too terribly scary either. That's actually good news. And it makes your life easier for later in the FRQ. So that's the main reason I'm going to assume they gave this to you in moles, so you had fewer calculations and it saved you time. So that's just kind of information about those numbers before I start doing anything with them. Does anybody have questions? Okay. So one thing you'll see I drew on there was I drew a little heating curve so you could think about what was actually happening. Since we started somewhere at 298, that's not yet at the melting point. So the first thing we have to do is heat it up to the melting point of our 933. And then we want to provide the energy that it takes to melt it. That's what it's saying in the problem, is we need to calculate the amount of heat to purify your 1 mole by melting it. So that's what we need to do. So we heat it to the melting point and then we melt it via the melting point. And so we know that this one, I need to calculate my amount of Q there, and I also need to calculate my number of joules there, my Q on both of those instances. But I'm going to calculate those differently, correct? How would I calculate my Q when I go from 298 to 933? Yeah, the Q mechanic. I have to take into account the change in my temperature. And how about when I actually am melting that aluminum? My heat of fusion. So I'm going to do moles times my heat of fusion. So now I've got 2 separate equations. I'm going to have to solve both of those and add them together. So let's solve. I'm going to call this one Q1 and this one's going to be Q2. So I'm going to work on solving Q1. And so we were working in classes. This is moles, and my mass and my specific heat was in grams. But since now they're both in moles, I can just plug those numbers into that same place, and I don't have to worry about doing any conversions or worrying about anything like that. It works out perfectly. So my 1 mole is going to be my M. My specific heat is going to be my molar heat capacity. That's going to be the same value. So that's going to go in here. Moles, Kelvin. And then my temperature change. I want to go from 298 to 933. So remember, we're taking our final temperature minus my initial temperature. So I have to take, because I'm running out of room, my change in temperature is going to be my temperature final minus my temperature initial. So I'm going to do 933 minus 298, which is what? Anybody do that? 635 is my answer to that one. So far, so good. So we found the difference in these two. Since I'm subtracting those as far as significant figures go, remember you're going to the least significant place. These both were able to measure to the ones place, so my answer still stayed measuring to the ones place. It happened to work out. It also has 3 sig figs, so that worked out both instances, but just kind of something to pay attention to. So then I go to plug my numbers in here, and now I just need to do is solve my answer. So if I get for my Q1, when I take this number times that number times that number, remember it was 15 something. 15,280, 240. Okay, and my answer here is in joules because my moles are going to cancel and my kelvins are going to cancel. So my value that's left here is in joules. And then this is going to be what my calculator gave me. Calculator doesn't understand how significant our figures were here in order to be able to round appropriately. So I need to round this a little bit so I have the correct number of significant figures. So here I have how many significant figures? 3. And here?
2.
And then here?
3.
So when I'm rounding by multiplication, I'm always going to round my answer to the least significant figures. So my answer needs to be rounded to 2 places. So I'm going to keep my 1 and my 5 and round it to 15,000 joules. So far, so good. Questions on that? Okay, so that's how I would solve for Q1. Can't be done yet because now I have to also solve for Q2. I've only put the energy it takes to get it to the melting point. I haven't provided the energy that it's going to take to actually melt it and go from a solid to a liquid. So now I'm going to calculate Q2. And so Q2, remember, again, has got to be my moles. And since they gave me this value in moles, once again, all I have to do is just plug in my numbers. So if I take 1 times 10.07, what do I get? Or just right here, 10.7, sorry. And then my answer would be in the units. Since those are moles and those are moles, my answer here is in kilojoules. So far, so good? What do I do with those 2 pieces of information? I need to add them together because I want to know how much energy it takes to get from here to here. So I have to do that number plus that number. So now I'm going to take, I'm going to move it over here. So I'm going to do Q1 plus Q2, and then that's going to give me my total amount of energy. So if I want to put together 15,000 joules plus 10.7 kilojoules, what's that? Why is that a problem? Yeah, I can't add joules to kilojoules. That's weird. So you can change it either direction. It really doesn't matter because we looked ahead and we know later in the game we're going to need to be in kilojoules. We're going to take this and switch it to regular joules. And for every, switch it to kilojoules. For every 1 kilojoule is 1,000 joules. So I'm going to drop my 3 zeros and it becomes 15 joules plus 10.7 kilojoules. And so now when I want to add those numbers together, that's going to give me 25.7 kilojoules. But because we're being worried about significant figures, I need to look at my answer. This one, since I'm adding, I'm looking at my least significant place. This one measures to what place? Tenths. And this one measures to the ones. So between those 2 places, which one's less significant? The ones place. So I'm going to use my 7 to round my answer up, and I'm going to get it to 26 kilojoules. Questions on that? Yes, sir.
Did you ever find out if you got
Don't.
25?
Hmm?
Did you ever find out, like, if you said?
I know I didn't look it up. Can you remind me what your question was? I can't remember.
I was just, so if I got 25.9, which is what you had.
Oh, would you get the point or not?
Yeah, would I get the point or not?
Yeah. I would guess so. I would think you would get your point mathematically, but like had this been a significant figure problem, which it wouldn't have been in this particular one, then that's where you'd be more likely to lose your points. But I am not sure. Could have put on my computer. Oh, if it were my test, I'd give you your points. Yes, ma'am.
How do you know how to be kilojoules?
I said it wouldn't matter. You could go either way. You could have gone either way. Because we've already worked through the whole problem and we know we're going to use our answer in kilojoules later, I went ahead and switched it to kilojoules now. But they'd have to accept either one because it didn't specify in the problem. Yes, sir. Sorry, I couldn't tell if you were playing basketball or.
For sig figs on when you're calculating the joules, what if you used number of one sig fig to find like 10.7? Then once you run it to one sig fig, even though the addition doesn't use one sig fig, it has 2. So like it's 15,000 times like quantity 1 times 10.7. So like it's 1.00, but what if it was just like 1 10 times?
Well, the AP people are not likely to give you just 1 because that wouldn't give you very many significant figures and that really ties your hands. So the likelihood is that's not the problem that would come up. But yes, if 15,000 only had 1 significant figure, and then when you got to here, you would have to have rounded it to the tens place. So then when you got to here, you would have had to call it 30 instead of 26. But yeah, you would have to follow your sig figs. Fair enough. But that wouldn't be proper science because you're not measuring as precisely as you can. I'm going to erase this so I have room to write. Is that okay with everybody? Anybody have questions on anything so far? Oh, sad news. Okay, and then do you want me to work out B or do we feel okay about B? Not necessarily that it's a working out problem. I'll definitely do C, but I just was curious if you wanted me to talk about B also.
So is it higher or lower?
You do have the answers. It's lower than expected, which a lot of people were able to deduce, or actually most of you guys had a good explanation, if I remember correctly. You all recognize that the calorimeter absorbed the energy. But sometimes you would think that that would mean that it took like higher energy, and that's not what would happen. So if you imagine that we have just this finite amount of energy, it's only going to be so much energy that can be absorbed or released from your reaction, then if some of it goes to the calorimeter, then the amount of energy that we measure is going to be a little bit less than what we expected because that extra energy went to the calorimeter. So that's how we kind of would deduce that information.
This kind of problem, your answer key has an answer that's really like shortened to the point. Like, is that all you really need to get the point? Or do you actually need to provide an explanation?
I have an explanation because it's absorbing energy. What further explanation would you like to provide? No, there's not a ton of questions. And this is what we would call the short FRQs. You only have 4 points. I know this one had 6 because I was trying to show you some more possible points. But on the AP test, you have several FRQs that are only 4 points. And you only have so much time to answer them. So you want to be as short and sweet as you can in your answers. It is a very fine line to walk. Am I writing enough versus am I writing too much? And that's one of the things that we're going to kind of work on. So for right now, I'd rather err on the side of writing more, and we'll kind of work on how can we pare it down between now and May, which we actually have some time. So it'll be okay. Yeah. Everybody good with B then? All right, so for C, if we were to compare our 2 different reactions, we have Al2O3, which is my solid. I'm going to drop my states of matter just because I'm being lazy. My aluminum oxide there is getting broken apart into Al and O2. That equation's not balanced. That's why it was being weird. Weird. Okay. Well, anyway. So we know this whole reaction going all over is going to be my delta H. And so that delta H there is going to be my 1675 kilojoules per mole. How are we feeling about the difference between delta H and Q? Sad. So it would be worth our time for a moment to talk about why Q and delta H aren't the same but are super close to the same. Yes? Okay. So Q is going to be equal to our number of joules, which obviously could also be our kilojoules. So that's going to be energy, and that's going to be in any given reaction. And so if it's a given reaction, then that means every time we run that, we're going to have to multiply it. We're going to have to calculate it. We're going to have to figure it out. We can't just come up with a constant number. Whereas delta H is going to always be the number of joules or kilojoules, typically it's kilojoules, that you have given a particular mole. So that can be a constant value. We can look it up in a textbook somewhere. So this one will always have to be calculated or measured or experimented in the lab. And this one is going to be a constant value. You'll always get the same answer anytime you do it. Because you can take the kilojoules you had per that given situation divided by your number of moles you had in that given situation. So here we calculated our delta H. And in our original problem that we did on A, we figured that if we were going to purify 1 mole of aluminum, that it equaled 25 kilojoules, right? 26 kilojoules? I guess I could just look at my sheet right here. So if that's my number of joules, that is my Q. Weird things I do. How do I turn that Q into a delta H? I have to divide it by the moles because I need to know the number of kilojoules per mole. And so in this instance, how many moles was it? 1. So that makes my math really easy. So now instead of my Q, it's now a delta H, and now it's 26 kilojoules per mole. And I'm going to use that answer. I'm going to compare it to this information up here. How many moles of aluminum did we make? 2. So it took this much energy to make 2 moles of aluminum. Are these two values comparable? No. So I need to make those comparable. What can I do to make them comparable? So if I divide this one in half, because that's how much it takes for 2 moles, and I only want to know how much it takes for 1 mole. So when I cut that number in half, I get 837 kilojoules per mole. And now I want to compare. This is the amount of energy it took when I was purifying it, so I was recycling it. This is the amount of energy that it took when I made brand new. So my 26 kilojoules per mole versus my 837 kilojoules per mole. Which one would be preferable? Why?
Because it takes less energy.
Good. 26 is less energy. And imagine, you guys know how much we're talking about. Energy is a high commodity. We want to keep our energy around. And the less we use it places, the better our futures are going to be. So here's AP taking a moment to explain why green chemistry is important and being on their little soapbox that they've got to encourage you to recycle your aluminum.
Okay, so is there any reason why the equation is not?
I don't know. And that's what I was saying.
Would that influence your answer whatsoever?
No, I don't know.
Because the ratio
I
is so
almost
different.
wonder if I just copied it over wrong or something. I don't remember what happened. So, because that's weird. That doesn't make any sense. I can pull it up from the AP thing.
The ratio would still be 2 to 1.
Yeah, I don't know if they just simplified it down for in there. I'm curious. I want to go look it up, but now's not the time. I would guess. I have no idea. I don't have a solid answer. That's when I put it up there. I was like, I don't know why that's not balanced, but I'm curious. I wasn't paying attention until I actually wrote it on the board. Do you have a question? So that would be our final answer. I can't remember. Justify your answer with a calculation. So which requires less energy? We would say purifying, and then here's our calculations. You could show kind of like I did here. It's a good way to justify that. Any other questions on that one? And I'm going to move on. Takers? Okay. So next up, so you guys want to do a little review on organic? Like hardly any. I mean, if you saw the AFL, there was only one question you actually had to know what an organic compound was in order to write it, and that was just that methane. In the AFL number, the last multiple choice one, you had to know what methane was so you could write its combustion reaction. So that's really, that kind of instance is what I'd expect you to know for the test, is like recognizing the names and kind of knowing how they go together, but they would just be related in a problem or some simple naming. So if you were looking at your carbons, meth is 1 carbon, F is 2 carbons, prop is 3 carbons, But 4 carbons, pent is 5 carbons. My arm is hurting. So when we talk about our carbons, how many bonds can our carbons make? 4. So if I told you it was methane, you'd know it has 1 carbon, and if it only has 1 carbon, then it has to have how many hydrogens? Yay. If you have 2 carbons, now that would be C2, so how many hydrogens would it have to have? Enthusiasm I hear out there is just astounding. Sorry. Yay for organic. I really do actually truly like organic. I just know you guys have a lot on this test, and this is so minimal, not where I want to spend a ton of your time today. But just, I'm happy to do that if that helps you guys. So then the other 3 functional groups we talked about in class would be fair games as far as like things I want you to be aware of in class, but not something I'm likely to ask you a question on, like, can you just name this organic compound? Mostly, I want you to just be comfortable with the basics of our organic. Fair enough? Joey, did you have a question? Did I answer it? Cool. Okay. Is that enough for organic, or do you guys want more?
It's not.
Thanks. Appreciate some response.
I'm the only one who ever responds.
There's limited number of responses in the class. I will agree with you there. So then lattice energy, we want to talk about? Sure. Yay. So look at that, more responses. That was exciting. Way to go, team. It's funny, you guys say you like these sessions, but it makes me feel like you don't when you just stand there and stare at me. I feel like I'm boring you. I can only be so exciting. I'm sorry. Okay, so NaCl versus CaCl2. So if we're looking at lattice energy, we're going to look at 2 things in order to determine their strength and their lattice energy. The first thing is going to be your magnitude of your charge, right? So here we've got our +1, -1 versus here +2, -2. Between those 2, which one's going to have the greater attraction? So this is a greater attraction between the 2. So that's going to win out because it has the bigger positives and negatives. We know that Coulombic attractions apply there. Now, what if they were tied? Let's say NaCl versus KCl, which I hate to use because we've used that a few times, but it's happening. So NaCl versus KCl, now they have the same charge, so one can't be greater or less in terms of that, so something else has to apply. What's the other thing that applies? The size is actually what it is, the size of your atom. And so between sodium and chlorine, if we were to look at our periodic table, sodium is higher on our periodic table than potassium. Did I say? Yeah, I don't know what I said a minute ago, but that's what I meant. Because when you're not comparing chlorines, because they're both the same. I feel like I might have said chlorine accidentally a second ago. But those are the same, so their size isn't going to play a role. Na versus K, Na is higher on my periodic table. So what does that tell me about the size of sodium? So if it's smaller here, and this is the larger one here, how does that help me to determine its lattice energy? Kelsey? Yes, yep, you're exactly right. Due to Coulombic attractions, the smaller sodium is able to get, exactly like she said, closer to your chlorine. And if your sodiums and chlorines are closer together, that provides a greater attraction. And so it's going to require more energy to break. So this is going to require more energy. So if we're going to put these in order, this would be the most, then the next most, and then the least.
So the you named that like Coulombic attractions. Is there like a name or a law for like the charges?
So that's still going to have to do with Coulombic attractions because it's about the fact that they have opposite charges, but these opposite charges are stronger than those opposite charges because it's basically twice as strong. Does that make sense? So I'd still go with Coulombic attractions.
What if you had 2 molecules that were 4 different elements? How would you compare them? And they have the same program.
What? Oh. Go with the smallest one overall and the biggest charge overall. So like I don't know, PbCl2 and LiF, something like that. Is that kind of what you're talking about, comparing those guys? So this has the bigger charge, so that's going to win out in this instance.
But what if they had the same charge?
Okay. So LiF and I don't know, so KCl, like that? Sure. So they have the same charges, and so these would still be smaller than these would be. And so, because they're both higher up on the periodic table than that one, it would be, if it happened to switch so that my fluorine and my chlorine were in different places, you would still just go with your smallest one because it's going to be able to get the closest into the other side. Is that kind of where you're going with your answers? So this would require more energy to break than that one would require because my atoms are smaller in size.
If the Cl and the F were switched, it would be small.
Still be the same thing. Still be the same thing because lithium still is smaller. So it's still able to get closer. It's still able to get the greater attraction. So you go with your smallest one. Did they get there?
Yeah.
Okay. Well, tell me if you have more.
You look at the first one. I was just kind of like look at the first element in the pair to kind of help your judgment.
I would look at the smallest one. This one happens to be the first, but it could have just as easily. I guess in this instance, fluorine would actually be the smallest, now that I think about it. Let me look at my periodic table. Yes, because lithium and fluorine are actually in the same row. Sorry. I told you a fib. Fluorine's going to be smaller because they're in the same row on the periodic table, and since it's further to the right, it's actually the smaller one. So between these four, fluorine's your smallest. So that's the one you would go with. I'm sorry. Other questions about that? Okay, then I'm going to maybe switch topics. Is everybody okay with that? Like, see, head nodding is acceptable if words out loud are not allowed. Let's see. I think we have left Lewis structures and polarity and all the stuff that goes with that. If you guys want to talk about it, or bond types and properties. Do we have a preference between the two? I don't remember. Lewis structures? Do you guys feel an agreement? Or how many people would like Lewis structures stuff? Bond types, bond properties, like ionic versus covalent versus metallic. Those are your thoughts. Lewis structures, hybridization. There's a good chance we'll have time to do both, but just which one do we want to do first? Okay, everybody who's pro Lewis structures? Everybody who's pro hybridization, or I'm sorry, bond types? I think Lewis structures one. So, Lewis structures are easy. Okay, well, we'll do.
Neither are easy. Do that bad. One's harder and one's harder.
Okay, so let's do ClI3. I don't know if this is a real compound in the world. I don't know. Okay, so I don't know. Internet world. I just picked this molecule. We're gonna go on the assumption that it is. I don't know if it is. Okay, so let's go with it. So ClI3, what goes in the center? Okay, and then I'm going to put my eyes around the outside. Okay, I don't know what just happened there, but you all just responded to that answer, and I just want to celebrate that for a moment because that was really exciting. Okay, so how many total valence electrons do we have? So we have 7 for each, and there's 4 molecules, which would make it 28. No, you're right. This was working people through where we got that. All right, so I first need to divide up my electrons, remember, so that the outside ones have the lowest energy. And the way we need to do that is we have to get each of those to 8 valence electrons on the outermost. So when I do that, putting 6 electrons, so 3 sets of lone pairs, plus the bond in the middle provides me 8 electrons on the iodine, and that iodine, and that iodine. So if I have 3 iodines all at 8 electrons, I have used how many electrons? 24 electrons. However, I had 28 electrons to start with. So that leaves me with 4 little electrons that have to go somewhere. Where should I put those?
On the CL.
On the CL. Okay. What? That is left, so I had to check again because after I forgot where chlorine was on the periodic table, I had to check on chlorine. All right, so this is a possible situation, right? Why is this possible? 2, 4, 6, 8, 10 electrons. That's too many on chlorine. But is that okay for chlorine? Because it's in the 3rd period energy level, or higher as far as energy levels go, lower as far as the periodic tables go. So that's fair game. This is an acceptable configuration. Now I've used all 4 of my electrons. I don't have to deal with double bonding or triple bonding because chlorine's already over the top. Why would we share it anymore? So that would be the correct Lewis structure. Questions on the Lewis structure? That's going to be the question I was going to ask. How many electron domains or what is my steric number? 5 is my steric number. So now I know it's going to be based on the trigonal bipyramidal set that's happening. But I have to think about how that's going to arrange my molecules because I'm going to replace some of those. I don't know if I can draw 2-dimensionally my 3. Oh, okay. So I have to, it's going to need to arrange itself so that these lone pairs can push the other 3 out as best as they can. So what ends up actually happening is you end up with basically a T-shaped molecule with your lone pairs kind of pushing down upon your other ones. I can't draw this 3-dimensionally because it's a 2-dimensional board, but you can kind of imagine my little bunny rabbit guy here is going to be a T-shaped molecule because we have my central atom with the 3 atoms around the outside, and then the lone pairs have to position themselves accordingly. So far, so good. Okay, so then, well, we established this is T-shaped. What would be my bond angle?
180, 90.
Good. See how it looks like it's 180 here and it looks like it's about 90 there. So those are the bond angles that we would pick for that particular one. How many sigma bonds versus pi bonds do I have going on? Good. 3 sigma. No pi. 0 pi. Hybridization. What's my hybridization? sp3d, because if I were to look at, I have 1 s, 3 p's, and 5 d's for each energy level, after the 3rd energy level, that is, and that's how many I'm going to have for each. And so if I have 5 electron domains, remember lone pairs count as a domain just as much as single, double, triple bonds do. And remember, double and triple bonds count the same as a single bond. So if I have 5 places, I need to grab my 1s, all 3 p's, and 1 of the d's. And so I'm going to make 5 brand new hybrid orbitals that we call sp3d. Okay, so those are all possible things you have to know from your Lewis structure. Let's talk about polarity for a second. So if we were to look at polarity, what kinds of things do we need to look at? Okay, so we need to know the shape. So I kind of tried to sketch the shape out so we could think about that a little bit. What else do we need to know? Electronegativity. So if we were to compare chlorine versus fluorine on its electronegativity, I'm sorry, chlorine versus iodine, excuse me. Which one's more electronegative? Which one did you say? You said chlorine. All right, Kelsey's being a cat and it's confusing me. Okay, so I need to distract you. So chlorine's going that way. My electronegativity is all going in towards the chlorine. So are we going to be polar, more towards the polar side of the scale or more towards the nonpolar side of the scale? More towards the polar side of the scale here, because my electrons are all going to end up in the same location. Do you remember those lone pairs that we were talking about up here? What are they really going to be doing to this bond angle? Is it going to be exactly 180? It's really going to be probably a little bit less than that, right? Remember, a molecule's probably going to be pushed down just like a smidgen, kind of a little curly T. So if you think about it, all my electrons are going to be up going here towards my chlorine. Happens to be up in this particular situation, but doesn't have to be. So the chlorine side of the molecule is going to become slightly negative because my electrons are going to be unevenly distributed up this way. Whereas down here, those is going to become slightly positive by where my iodines are because my electrons are distributed unevenly. So it's really important that you kind of remember that that electron distribution is important, but so is what the shape of your molecule is, because that can make a big change to it as well. Let me say something else. Just do not remember what it was. Questions you guys have? I don't remember what it is. Polar versus nonpolar. You guys, one of the ways that we've talked about you could remember it is if it has lone pairs, like in this instance, it's more likely to be polar. If your outer atoms are different, your terminal atoms are different, it's more likely to be polar. That's a great tool for you to put in your belts of, I need to remember whether things are polar or nonpolar, but that's very unlikely to be the question that is asked. We might compare two different compounds, or we might have to say where the charges are located, or use it. Next unit, we're going to use it a ton to talk about how the different molecules are going to interact. So those are the types of questions you're going to get. If somebody were to ask you about why something's polar, please don't ever use those as the reason why. Those are not the reason why it is polar. It is not polar because it has lone pairs. It's polar because it has an uneven distribution of charges. That's going to be due to the electronegativity and the arrangement of your atoms. So part of having lone pairs allows your molecules to be arranged slightly differently, but please don't say it is polar because of the lone pairs. So everybody caught that. Please don't say that. Okay, you want to talk about bond properties for a minute? Or 10? Can I erase this? Do we do another one? Okay. Okay, so we want to try to go through our bond properties as quick as we can? Or do you want me to do another Lewis structure? Okay. Bond properties. So we've got ionic, we've got covalent, we've got metallic. And then we have within our covalent category, remember we have our molecular and we have our network. But those are both going to be our covalent. Do you guys have a question? No, I'm not.
Yeah,
Is there something I can help with?
it might be a bad question, so we're trying to figure it out first.
Do you know that like, this is a safe place? This is where we ask questions. That's actually the whole point of this activity here.
Okay, so you're talking about how Cl can hybridize because it's lower on the periodic table. But we were wondering like, where the cutoff is for that.
Third energy level. And so the reason behind that, if you remember these little diagram guys, where we like fill in the arrows, remember that? So the first energy level has just the s orbital. The second energy level has the s and the p orbital. And the third energy level has s, p, and d. So the third energy level is the first time you have the d orbitals, and it's the first time you're able to bond more than just the 8 electrons. Because remember, you can put 6 here. So these levels, you can have 2, 4, 6 electrons. So that's as much as it can hold. And so hydrogen and helium only have the 2 places to put electrons. That's why they can't bond anymore. I think that was a great question. You're welcome. Okay, so just want me to go through the bond properties? Is that kind of where we are? Do we have questions about it? Are there particular ones you're having a hard time of knowing or remembering? I think one of the things we talked about specifically was volatility. So I'll answer that. Kelsey, do you have?
So IMF bonds, molecular, they're weaker than, they're the weakest bond, right?
Yeah, so covalent bonds, while themselves between atoms are the strongest, they can use the intermolecular forces And so when we go to break those, it's very easy to break because they're more just forces and not really strong bonds. So that's why our molecular bonds have a low melting point, because it's breaking the intermolecular forces. And since they have a low melting point, that's why they're very, very volatile. Volatility means that it breaks apart or evaporates really easily, or that it's basically the ability to evaporate. So if it's very volatile, it's going to evaporate very easily. So it has to have bonds that break easily. So we're looking at the fact that it has the intermolecular forces that are able to be separated. If you've ever heard of somebody who is volatile, so we use this explanation, like a volatile person, you can make them mad really quickly. So it's like, doesn't take a lot of work for them to yell and scream at you. Same deal here. Doesn't take a lot of work to get a molecule to evaporate that's highly volatile. So it has to have weak intermolecular forces, which means it's probably going to be a molecular solid or molecular covalent compound. Doesn't have to be a solid. Kelsey? Yes. So as far as all the intermolecular forces are just intermolecular forces in general. So our strongest one here is going to be our covalent. And your network would be a little bit more than your molecular. And then, so next on the list, there's some debate on the next two. Ionic and metallic I would put next, kind of back to back. We would typically think about them in equal strength between the two of those. And then way down much further would be your intermolecular forces. Huge, giant change in between these two. And next unit's where we'll talk more about intermolecular forces. And so if you're curious, hydrogen bonding, dipole-dipole, and London dispersion would come next. We'll talk more about those guys. Okay, yes. Let's see, what other some common ones? So we talked about why networks molecular solid is so much low melting point, high volatility. Ionic compounds have to have higher volatility or a high melting point because of the fact that they have really strong bonds. So their high melting point, it's much more difficult to melt an ionic bond, and it's a very high melting point for your high melting point. So a very, very high melting point for those two, because you have to actually break the bonds between atoms, as opposed to here where you're breaking your intermolecular forces. Your ionic bonds over here are more likely to dissolve in water. Since they're more likely to dissolve in water because you have these charges that can get attracted to the polarity of your water molecule. So that means it's more likely to dissolve. Over here, you've got your metallic compounds that have those delocalized electrons. And since they have delocalized electrons that are moving freely, that free moving electrons allows them to grab light and then reflect that light back out so it can be shiny. It also allows for there to be openings for electrons movement to go. So that's why it's very, very highly conductive, because it allows for transport of electrons anywhere, like as a solid. Over here, because of the charges, it allows for transport of electrons when it's dissolved in water. That's why ionic can sometimes be conductive. So my delocalized electrons, oh, that also is why it can be malleable. Malleable, if you think about it, you can squish those down if you've got these positive electrons that are being surrounded by all these free floating electrons. So as I go to push those down, I can really just like condense them all together and form that into whatever shape I want to because of that free moving electron. So those are kind of the properties that would come from that. Molecular, I had several people ask me yesterday why covalent can dissolve and not dissolve. So remember, that has to do with if it's polar, then it will dissolve in water. And if it's non-polar, it's not going to dissolve because water itself is polar. So only things that are the same polarity are the ones that are likely to dissolve. Any other questions for me? Yes, Tina? More likely to dissolve because it has charges, and so it can be attracted to those polar bonds that we were talking about in water molecules. So that allows it to be able to dissolve. Other questions? Other questions? Okay, let's call it a day, and I have a couple papers.